Welcome to this tutorial, guys, and it's a pleasure again to be with you at this time as we are going to talk about trees implementation in data structure. A tree, first of all, we need to understand what is a tree. In normal life, we know a tree in Kinyarwanda is what they call igiti. Usually the tree will be having the roots and also the branches. As we can say, there's some types of trees that can have branches, and then when you smart the branch from the tree, then also you plant it somewhere, then also it becomes a tree. So it means then we can have a tree, a big tree with those branches that we can also call subtrees. So in a database, a tree is also represented as one-to-many relationship. So it means one parent here, and this one parent will be this one parent can be having, like, this is a parent and this is child 1, child 2, child 3, child 4. You can see that this is a one to many just because this parent has been given this many children. This child also, when it becomes, or when he or she becomes to the age of reproduction, then also she can have other children all together. So then this is what we mean by trees. So then when we go to this, through this, usually trees are being used when you want to implement or to build a database of grandfather's descendant. When we say here we have a grandfather, and then what are the children and who is the descendant of the other grandfather. So here we also work on it when we want to build a corporate structure, or what many people are calling organization structure, where we can have the, like, MD here, and the MD can have another department here, and this department here, and another department here. This department is divided into some divisions, these divisions, and this. So you can understand then when you want to work on corporate structure, because we'll be having the super or the top administration and also till the low level of administration, the same of government, as we can have here the president, until we be going till a local citizen. So then here, when we want to talk about trees, we need to understand about these definitions or terminologies. You can say this is the root, and the root is having B and C. So it means B and C are children of A. So the root, usually it is the topmost node, and all of these nodes, as we can see, they are connected with edges. So then here we can see that then A is a parent of B and C, and we can also say B and C are what? Are siblings. They are siblings. Why? Because they are coming from the same parent. And we can say also D and E, they are also siblings, because B, it is the parent of D and E. Again here you can see that this is what we call in French cadet ou cadet, and in data structure or in database definitions we call this leaves. These leaves, those are leaves because this is a leaf and this is a leaf, because they don't have children. And together here, when you say this one, so A is a grandfather of E. In other words, it is the ancestor of E. And also E is the descendant or the grandson of A. And also here, as we can see, we are having some levels. We can say this is level 0, this is level 1, and this is level 2. So we are having also levels, and also we can have also the number of nodes connected to a particular parent. Like here, if it is the parent, okay, what is the degree of B? It is 2. What is the degree of A? Then you can say them. Usually the degrees, those are the number of nodes that are connected to a particular parent. As we have said, then we need to keep track what is a root. The root, it is a node without a parent. A leaf, it is the last node without a child. Interior nodes, those are the nodes in between. They are not leaves and they are not roots. And also we can say what is the distance from root to leaf. Then we can say what is the height. The distance, like here, the distance is 3. So then here we can say, okay, a tree is nothing other than a finite, non-empty set of nodes. When you say finite, it means it is something that is not infinite. It is something that we know the starting and also the ending. And also each node will be connected to another using an edge. Connected. They are connected. They should be connected to the root. And also there should be no cycle. Like here, we cannot say that this is, for example, C and this is, for example, A, and we come here and then we say again C have given birth to A. Impossible. Here also, it can be proven that a tree has one less edge. Let me say, for example, how many edges do we have here? 1, 2, 3, 4, 5, 6, 7. How many nodes? 8. So it means then the number of edges will be equal to the number of nodes minus 1. Edges is equal to the number of nodes n minus 1. Again here, we can say, is this a tree? Yes, because each and everything, they are connected and there's no cycle. Is this a tree? No. Why? Because this is not connected anywhere. Is this a tree? Yes. Even if we are having here 3, so we didn't talk about the restriction of suns. Is this a tree? No. Why? Because there is circle. Here, the cycle, he will be making this not to be a tree, but to be a what? To be a graph. We'll be talking about this in our next tutorial. And then here, is this a tree? Yes, there's no cycle, and there is also no node which is not connected. So we can then talk about this. This is a subtree, and this subtree is having, this is a tree, sorry, and this is the root, and this root is having this right subtree, left subtree, and right subtree. So a subtree, usually it is the same as the tree, but also that is connected to another node. So here we can say then a tree, it can either be empty or having 0 or more subtrees. So when we have like this, is this a tree? Yes. Is this a tree? Yes. Is this a tree? Yes. Like this is a tree, and even this only is a tree, and this only is a tree, and this only is a tree. Why? Because we've said that a tree can either be empty or have 0 or more trees. Like here, when we say then this is the root, and the root is having 2 children, and these 2 children, because they are coming from the same parent, they are siblings, and these are the leaves. And then here, these are the interior nodes. So when we talk about then the depths usually, it is the path length from the root to the tree of the node. So usually the height of a node will be the maximum distance of any leaf from this node. You can say, what is the depth of this one? It is 1. We'll be talking about this when we'll be talking about a Viera tree. So then here we are having too many types of tree, and those types of tree we can have binary tree, and also what we call Matson's tree, and also we can have other trees which we call forest tree, we can have a Viera tree and something like that. But let us first make our emphasis on binary tree and a Viera tree, and also multi-sans tree. So then binary tree is what? Binary tree is a tree with 2 or 1 or 0 children. So it means it can have at most 2 children and at least 0. So like here, this is a tree. But is it a binary tree? Let me see. This is 1 node and it is having how many children? 3 children. Impossible. It is not a binary tree. Is this a binary tree? 1, 2 children? Yes. This one also 2 children. This one also 2 children. This 0 child, 0 child, 0 child, 0 child. So we are having only 2 and 0. So it means then it is a binary tree. So then in binary tree, you can say a full binary tree. A full binary tree, it is a binary tree which has exactly 0 all 2 children. If, for example, we don't have this, yes, it is a binary tree, but it is not a full binary tree, because full binary tree should have 2 children all 0. Like here, if I move this, then this one will be having only 1 child. So a full binary tree, it will be having the height of 2 power 8 plus 1 minus 1. So usually here, this is an example of a full binary tree. Then what do we mean by a complete binary tree? But then before this, a binary tree is a full binary tree if each non-leaf node has exactly 2 children and the leaf node has identical path length. It means this one, the length will be the same, and all the nodes which are not leaves should have 2 child. So is this a binary tree? No. Is this a binary tree? Usually this one, it is not a binary tree. Why? Because of this connection, there is no way B can give birth to D and D give birth to B. This is not also true. So then what do we mean by complete binary tree? Complete binary tree, it will be a binary tree with at least 0, at most 2 child, and also if we are having any one child, it will be going to the left. So for example, if this one is not here and it is here, it will not be a complete binary tree. So if it is one child, it should be going to the left. So is this a complete or not complete? It is complete. Is this complete or not complete? It is not complete. Why? Then here we can say, is this complete or not complete? Usually, as you can see then here, level 2 is missing. As you can see, this one, it is having too many levels more than this one. It is not complete then. Is this complete or not complete? Not complete. Why? Because of this level 3. Is this complete? Is it a complete binary tree or not complete? Usually then let's just talk about binary tree as it is itself. So when you say a binary search tree, now it is a type of binary tree, but all the left elements will be less than the root, and the right element will be greater than the root. So smaller values should be going in left and the larger values will be going in right. So it means here x is greater than y, then y will be here, and x is less than z, then z will be in the right subtree. A binary search tree, usually it will be a binary tree with these properties. The properties will be all the items in the left subtree are less than the root, and all items in the right subtree, they are greater than the root, greater or equal to the root. And each subtree is itself a binary search tree. So it means this criteria should not only be applied to this first, but also it will be applied to the remaining subtrees. And also here we need to say an example. Is it a binary search tree? Let me see. If 10, so it means the value from here should be less than 10, yes. Greater than 10, yes. Let me come here. Left, it should be less than 10. Right should be, yes, true. 30, 25, 45, true. Let me say this, 5, 2. Yes, 45, 30, 10, 25. True. It is true. Then we come here 10. 10, 5, true. 45, true. 2, true. 25, false. Why? Because usually this 25, it is greater than 10. There's no way it could come here. It could have gone here, and then it comes here. So then here we can have, is it a binary search tree? 17, 22, 19? No. Why? Because there should be the rotation. Is this okay? This from here it is true, from here not true. This not true because of here. This true. Then we come here true. 22, 22 not true because it could have come here and even just be put here. 22. So then an aviary tree. Then what about an aviary tree? An aviary tree will be having these conditions. The first condition, it should be a binary search tree. A binary search tree, as we have seen, it has to be having all the left element less than the root and right element greater than the root. And also there should be the balance factor. That balance factor should be 1, 0, and 1. And the balance factor is found by subtracting the height of left subtree with the height of the right subtree. So what do you do then in order to have an aviary tree? You do the right rotation, left rotation, right rotation, or left rotation. So this one then, we are having like 10, 20, and 30. This is an example. And usually this is from here, it is a BST. True, this is a BST. But then we need to check, is the balance factor -1 and 0 and 1 to all the nodes? Let me check. So here, right is 0, left is 0. 0 minus 0 is 0. This one, left is 0, right is 1. Then 0 minus 1 is equal to -1. Then we come here, left is 0, then right is 1, 2. Then 0 minus 2 is equal to -2. And we have seen that -2 is not in the set. What do we do then? You need to do what we call a left rotation, and you take this, it becomes like at the top, so it means this will be going down. So it will be 10 here, and we connect it to like this to have like this. Now let us check if the solution is there. Is it a binary search tree? Yes, because left is 10 and right is 30. Then we see what is the height of left minus right. This is 0 and this is 0 and this is 1 minus 1, which is also 0. Then from here we don't have any problem. It is now an aviary tree. Let's see then, we have 40, 20, and 10. It is true. This is a binary search tree. But we need also to talk about the balance factor. So this is 0, this is 1, then this is 2. How did I find this? This is null. It means then also this is null. So 0 minus 0, it is 0. So we have this. This is 1. This is 0. 1 minus 0 is equal to 1. This is 1, 2. 2 minus, this is null, then minus 2 is equal to 2. So then we need to do what we call a right shift, right rotation, sorry. Then this one will be going here down other than going up. Then it will be right here 40 to have this. Then as we can see now, we are having an aviary tree. Assume we had like this, the root is 40 and in its right we have 20, and the left of 20 we are having 15. True. This is a binary search tree, but is it an aviary tree? Let me see. This is 0. Why? Because its left is 0 and its right is 0. 0 minus 0 is equal to 0. This is now 1. Why? Because this is the left is 1 and the right is 0. 1 minus 0 is equal to 1. This is 2. How? Because its left is 0 and its right is 2. Then 0 minus 2 is equal to minus 2. So it means it is not an aviary. Then what do? The first thing to be done, it is to say, okay, let me first make it at as this first one was. This. So what should I do? I can say, okay, let's then I start with 10 with the right rotation, not left. It is right. Sorry, right rotation, right rotation, and this right rotation, it will be making us to have 10, 15, then 20, which is this one. Then from here we are having a BST, a binary search tree. But does this has the balance factor which is falling from -1 to 1? No, because this is 0 as I have told you. This is -1 and this is -2. How have we found this? The left is 0, the right is 0, then 0 minus 0 is equal to 0. The left is 0, the right is 1, then minus 1. It's because it is 0 minus 1. This is 0 minus 2, which is -2. So then after this, we need then to do again the left rotation. Then we have this. What about then this? What about then this? We're having 40, 20, 30. It is a BST. But then we need to check this one. If I just come and I put it here, then what we need to first do the left rotation, not the right rotation, but left rotation. Sorry. Then here it becomes on this line. Is it still a BST? True. 30 at 40, 30, 20. Then we do here the right rotation so that we can have this one. Excellent. So usually the deletion will be the same as BST, but also we need to maintain the balanced subtree. We need to maintain the balance factor, which will be falling from -1 to 0 and 1. So let us go then to BST operation. So we can have traversing, and in traversing we can have in order traversal, we can have post order. We'll be seeing this. How do we do it? And we can have also pre-order. So we can have all of this. In insertion, in searches, we can search for a node, we can insert a node, and we can also delete. So it is what then we are going to discuss about. Traversing, we can have pre-order. Pre-order means you will go from root left right. In order, it will be left root right. Post order, it will be left right root. So it means if we are having like 1, 2, 3. So it means then using pre-order, you will be displaying 1, 2, 3. Using post order, you will be displaying 1, 2, 3 like this, or it will be 2, 3, 1. Using then like this is, let me say for example, this is our tree. Using pre-order will be displaying, using pre-order of this pre. If it is pre, we'll be displaying what? Because on pre we'll be first of all visiting the root 2, then we go to the left 1, then 3. Using in order, it will be 1, 2, 3. using post order. Post order, because we start from the left, it will be 1, 3, 2. We'll be seeing in general how does everything works. The first thing for pre-order, we need to visit the node or the root, then we go to the left, then we go to the right. Post order, we go to the left, then right, then root. And then in order, it is left, root, right. An example here. Let us see then using pre-order. As we have seen, pre-order, you need first of all to visit the root, then you go to the left, then you go to the right. So here, what is the root? 23. Then we'll be writing 23. Then we go to the left. Then the left is 18. Does 18 has another left? Yes. We go to 12. Then, does 12 has another left? No. Does 12 has right? No. Then we go to right of 18. Then we go to 20. Then after this, does this have another one? No. Does this have another one? No. Then we go to the right, which is 44. 44. Then we see it's left, 35. Then it's right, 50, 52. Then what about post order? As in post order, we have said that we need to go to the left, right, then root. Then 23 is the root. Does this root has another left? Yes, it is 18. Does 18 has another left? Yes, 12. Does 12 has another left? No. Then means we need to display 12. We go to the right. Does 12 have a right? No. Then we go to the right of this one, which is 20. After 20, then we go to its root. We go again. We go to the right. This right, we have said that we need to go to the left right root. So it means we'll be starting with 35, 52, then this one. So the root, usually the correct root or the grandparent will be coming last. In order, it will be 12, 18, 20, 23, then 35, 44, then 52, because we'll be coming like this. We'll be coming like this. Okay. Then here, the right node, left traversal. So we are having other types of traversing, and also we can talk about arithmetic expressions using binary tree. So when we talk about this, usually we can say, let us use in order traversal. And in order, as we know, we will be going from left to right root. So it will be A divided by B times C times D plus E. All of this, we'll be seeing them. How can we use arithmetic operations in this? So it means then here, as we have understood, so we need also to know the codes, how the codes are being written. So usually these are the explanations of the codes, but then what I want them to explain one while I am doing these things, because it is the good thing to be done in the codes. So I want them to start with the codes. Usually there's some codes that I've been writing. There's some codes that I've been writing, but then let us have our own codes. We are going to write the codes to see then how everything is working. So here, I want them, first of all, as we know, we are going to use C programming. And then we need to include Studio. Studio, we have said that it is a library. It is a library, and this library, it will be giving us access to input output. Let me call it tree implementation. So in our tree implementation, then we know that the first thing that we need to do is to create our structure. So let me create a type def structure, and my type def structure will be having some members, and these members of mine, they are going to be int info. Then here I will be having also struct node left. Node, I'll be having my left. This is a pointer that will be pointing to my left subtree. And here also I will be having my right pointer. So as we can see then here, as we can see here, this is the definition of my structure. The first thing that I am going to do, I am going first of all to make my root, or to make my tree, to start my tree. Then here I can say okay, struct node, and I am going to call it, let me call it make tree. And in my make tree, usually it is a function, and this function of mine, it is going to have a value to be inserted. And when I'm going to insert a value, usually here I need to create a pointer, and here the pointer I can call it, okay, let me see, struct node p, and I am going to allocate this dynamically using malloc, and my malloc will be having the size of, and this size of to be the size of struct node. So here I need to type cast my struct node, my pointer into struct node. Why? Malloc usually return void pointer, and me I want struct node p to be returned. So this is why I need to type cast. Again here, after allocating this, I will say then p dot left. My p dot left is going to be equal to null, and my p dot right, it will also be equal to what? To null. But then again here, we say then my p dot info then will be equal to what? My p dot info will be equal to value, but this p is like this. So you can see then I have finished to do what? Let me format use this. I have finished to create my root, or to start with my tree. Usually if I am to say, it is like saying that I have gone here and I have created a node, and its left is null and its right is null. Then here I have putted some data. This is like what I have done. Like coming here, creating, then you put here the root, and the left is null and the right is null. After this, then I need to say, how can I set left? How can I set right? Usually it depends on what you want. You can say, I want to set left, I want to set right. But for me then, what I want to do, I want to show you how can you insert anyway. Remember that this is what we are creating a binary search tree, and we have said that this binary search tree, it is working as this. We can say that all minimum element will be coming in the left, and maximum element will be coming in the right. How do you do it then? Let me say I am then to create another function, and this function of mine, it is going to be insert, like insert anyway. Let me say insert anywhere. My insert anywhere will be having something like struct node, and my struct node is going to be struct node, for example, root. Let me say, for example, this, and also my int x. So it means then my x, the way it is going to be done then here, what am I going to do? I will first of all check, is my root nar or not nar? We say then if root is equal to null, what do we mean? So it means then it is null. We don't need to go to the right, we don't need to go to the left. I need only to call this, but then I will return it. I will say return, then I will return make tree, then after returning it, but I will be passing x in it because I want it to be done from there. After this insert anywhere, then here I will have, then after this if, I will be having my else if, and in my else if here I will say, okay, what do I want to check then? I want to check if the number to be inserted is less than root.info. So if x is less than root.info, what should I do? Remember, my info is the value, then I want to check if root is greater than x. Root info dot is greater than x. So it means then if it is the case, if it is less than that, I need to go to the left. So then here I need to say then root dot left is equal to the same function. I want to make it recursively go to root dot left, then I go back and I insert x till I will be going where I need to insert. So I have another else if. So copy and I paste it here. So this is my else if. Then here I need to check if it is greater. I say else if then x is greater than root.info. I need to go to the right. And here I need to go to the right till it will be till the condition will be false. So this insertion will be helping me to insert anywhere, but then after everything I need to return something like I need to return root. Because why returning root? Because this function of mine, it's a pointer of struct node, so I need to return something of struct node, and root is of struct node. Then here we can say, okay, I want them to see how can I display. As I have told you, we need to know which display am I going to use. Let me say, for example, we are going to start with display using in order. Let me say void, let me call it display in order. When I'm going to display in order, I will need struct node root. I will need struct node root. So after this, what should I do? I can say, okay, I only need to say if root is not null. Why? Because we cannot display from null. If root is not null, it is when I can start. Otherwise, it is not possible. Else, I can tell to the user printf let me only say done. It means nothing to be done. I'm already done. So then here then I will say, okay, if it is the case, I need to call this function display in order, because I need to first of all go to the left, which is equal to root dot left till I will be reaching to the left. Then when I reach to the left, I will print something, printf with the value, which is for example d, and I can put this t so that it can give me a space in between. Then here I will be displaying root dot info. So after this, then I need to go where? I need to go to the right. So you can see this is my display in order. We can ask ourselves then, how can I write another function to display in pre-order? Let me, for example, post order. Let me say, for example, display post order. Let me say, for example, display post order. Display post order. So it means in display post order, I need to first display. I need first to go to the left, then to the right, then to the root. I need to cut this here, then I paste it here. Nothing difficult. So you can see display post order is now done. So we can say, we can ask ourselves then, how can I search? Let me say, for example, you want to search. Let me say struct I'm going to call this search. And if I am going then to search, let me say, for example, because it is becoming green, it means it is a keyword. It is known by the system. I need first of all to come here and then make another thing to change it to black, back to black. So if I am going to search, I will need two things. The first thing, it will be the search key, and also the tree. In which tree do you want to search from? So then here it will be x. Let me call it x of key. Let me call it key. Then from here we can say, okay, which key do I need to search, right? So okay, if then here I need to search if root is equal to null, all, because we can have another version, or root dot info is equal to the key. What should be done? I need only to return the root. I need to return from there, and I return what? I return root. So I can have then another if. I can say, okay, if then it is not the case, and but the root dot info, my root dot info is less than the key. If it is less than the key, so it means I need to search from the right. So if it is the case, I need to say, let me call back this search node, then I return search node, but going to root dot right, and also I pass the key in. Excellent, very good. There's nothing difficult from here. So then here, after this, I can say, okay, otherwise, what is this? Let me even remove this one. So otherwise I can say let me return to the right, to the left. This is like saying else. As you can see, this is my if and this is my else. So it means I have finished to search. Searching, you will see, okay, if root is null or root info is equal to key, you will return root. Else if root dot info is less than the key, you need to go to the right. Then on your else, let me put another if so that we can understand very well. If, so that we can understand very well. Then if now it is greater, what should be done? It means we need to do like this. Let me format. You can see that if root is equal to null, I will return root, or if root is equal to info, I will return root. If then it is less than the key, I will go to the right, and if it is greater than the key, I will go to the left. Very good. Then here, this is it. This is not it. I need to come here, and then I say this. Well and good. So now you can see that it is very good. Yes, so it means then my search is now finished. Then I can say, okay, for example, I want then to destroy. Destroying the tree, it will not take much time. It will only destroy. So let me say destroy the tree. If you want to destroy the tree, then you will only need the struct node, then let me call it root. By this root, it is a pointer. So then after this, I am going then to destroy. So usually if you want to destroy, you need to destroy when your root is not null. So then if, let me say, if my root is not equal to 0, then I can destroy the tree starting from left, right, then I destroy. I can say, okay, destroy the tree. You are going to destroy the tree by going from root dot left, then copy paste, then I go to the right side. After the right, I will then need to free my root because there is nothing remained in. So you can see I have finished. I don't know what is happening with my mouse. So as you can see, I have finished to destroy my tree. So we can do too many functions. Let me say, for example, find minimum. You can say struct node, then find minimum. If you want to find minimum, you need only the tree. If you want this, you need to use the tree only. Then in your tree, as we can see, what do I need here? I need to say if the root is not null, it is when it can be done. If then root is not equal to null, then it is when I can do everything. So what should be done? So if root dot left So if we are still having something at left, this is what I am saying usually. I need to go again to the left, because usually in a binary search tree, the left of all left, it is the minimum. In binary search tree, the right of all right, it is the maximum. Then here, then I need, if it is the same, if it is the case, if I do have something again at the left, I need to call back root dot left till I will be reaching to the left. Yes, again here, if then there is nothing, but there is something, then on my else I need then to say nothing, because I have finished to find what I wanted. I don't have a condition, but then here I will say printf, let me say for example percentage %d main node is percentage %d, then I do what, I go here to the root dot info. So where I will be reaching, it is where my left will be. So otherwise, not otherwise, and else I will also return root. So after everything like this, here I have return and here I have return, there is no problem. So the same, you can see I have been able to have my find minimum. So how can you find maximum? The same. What do you need to do? Find max, you will only go to the right, and after having your right, then you display your info. Finished. So we can have too many functions, but then for us, let me see whether we don't have some errors. Usually we are having some errors. We don't have an error. We have an error here. We've used P in uppercase. Yes. Here we only have warnings. But warnings also, you need also to take care of them, just because they usually can reduce the performance of your system. So let me say that, okay, here I am going to go to my main menu. So let me say int main, and in my int main I should return something, right? Like return 0 because it is int. So after this I am going to come here, then I say, okay, I'm going to say printf welcome to BST operations, then /n, please choose from the below. Again, I say like this. After this, I can say, okay, nothing to be done. Welcome to these operations. You can put another n, and here I say, okay, like this. This is usually what do I want? What do I want here? As you can see, okay, it is telling me warning, make tree, okay, destroy tree before return. It is expected to have a semicolon before the return. What do I want here? So printf, the reference for printf, I need to use p. Okay, welcome to BST operation. Please choose from the below. Only that I can increase this number, the number of this. Okay, no problem. So then here, what should the people then choose from? Then here, what do we need to choose from? I can say that, for example, I want one to make three. Then I go second, insert value, then 3, display in order, then full. Let me say that, for example, full it is exit. But as you remember, we have too many. We have too many functions that you can include in here, like all of these: find min, find max, destroy tree, search for a node, display post order. All of these, they are there, so you can also include them. But me, I don't want even just to have all of this. Then I only want like these three. So calling a function is not an issue, but defining a function is what matters. So then here I need to rescan if the choice of the user. Then here the choice usually it will be, let me say it is ch, and this ch of mine, it should be an integer. Let me say, for example, here before everything I need my int ch, and also here let me say, for example, I also need my int value. After this, remember that also I need a struct node that will be passed, and let me call it temp. Okay, so this is my main. Then I am going then to switch. Then what should I switch? I'll switch ch or my choice, and in my choice I will be having some cases. So my case 1, then what will be case 1? Case 1, I said make tree. I need to go there and then see what is the okay, it is also called make tree. Make tree. But then here I will just ask to the user, if choice is 1, I will ask him printf enter the value to insert. After this, I will need them to scan if. Then my scanf will be %d, then I receive the value. After this, I need to call my make tree, and then here I just call it with value. So it means I have finished. So then here we need to see on our case 1, then we can say, for example, we can say that, for example, we don't want this, but we want then like temp only to be equal, without even just calling, is equal to make tree value. So this is my case. Again, after this I need to break. So I can say that, let me have case 2 again, back. And on my case 2, remember that my case 2, it is to insert a value anywhere. The same, I'm going to copy this, and then on my case number 2, I will say, okay, then is it okay, I will say, for example, okay, after this I will call my function, and my function is going to be what? It is not make tree, it is insert anywhere, I think. Insert anywhere. So here I will just call insert anywhere, but in my insert anywhere it will need temp together with the value. Then I break. Then my case 3, it will be only display. Then on my display I will only say it is display in order. Then I will come here and I copy this, and in my display in order I will pass something like temp init. After this, then I will break. So my case, the other case is what? The other case is case 4, and my case 4 usually to be having nothing other than exit, and I pass an argument in my built-in function which is exit. Then another case, it is the default case, and in my default case I'll be telling to the user that error in choosing. Error in choosing. Then in my error in choosing, then I can tell him, okay, please enter the correct choice. But I want all of these things, like here from here, welcome to BTS. Then here I can use a while loop. Then here I say while 1, and everything should be included in here. Then I close it from here. Let me see. As we can see, yes, we have everything. So then here, as we can see, oh my goodness, what is this? Okay, it's true. Okay, then here we can run to see, okay, welcome, and then enter your choice. So please scan if your choice. Okay, I need to come here and then I put it choice before I say exit. Then here I tell him enter choice. Then after this, let me come here, then I run. So enter your choice. Let me say, for example, make 30, and I'm going to add 35. But then like here, as we can see, my value, the way I received my value plus there is an error. I need to come here, then I see, okay, here when you are receiving the value, then you need to put this % sign. I save back, then I come here and I run back. Enter choice, it is 1, which is make 3. Then I say 55. Enter your choice, it is insert. Then I'm going to enter 23. So usually if, for example, for the first one, for the first thing it was for the first time it was, let me say, for example, okay, for the first time it was 55, right? Secondly, what is going to be done, I have putted what was the input, I have putted 23. So it means 23 should be coming left. So let me say the third time I'm saying I want to insert, and I insert, for example, 30. So it means then 30 will be coming here. Let me say, for example, next time I'm putting 15. Insert, and I'm putting 15. So it means then my 15 will be going where? My 15 will be coming here. Let me say that, for example, next time I'm putting 60. 2, then 60. Then my 60 will be going where? My 60 will be coming here. So it means, what do we have here? The things that we are having this, and this. So if then we are going to print using in order traversal, what will be the output? In order will be first visiting the left, then the right, no, sorry, the root, and then the right. Then we need to go back to the root, and then 60 after. This is our in order traversal. Sorry. This is our in order traversal. So then if I am going then to place 3, it should be showing me 15, 23, 30, 55, then 60. Wow. So then it means what only I have done which is not correct, it is this done that I have wrote on my printf. Such a node, okay, post order, this else done, it is not there, because as you can see it is also being displayed. So only this, my in order, and let me say that I wanted just to have like this. So let me check back. I'm just putting, for example, 40, make 3, 40, 30, 20, 70, then I'll press 3, which is display. Wow, my display, it is only bringing for me 40. Why is it only bringing for me 40? Why? We need to ask ourselves then why do we have this? Usually there's no else. The else, usually I don't want else. Then here, let me say, for example, I want to insert, make root, then I enter 45, then to this, to this, to this. Let me say, for example, 3. You can see that everything is coming. What shows you that it was correct? Usually when you display in order, it becomes ordered automatically. So thank you so much. Thank you for watching this tutorial. I think then I will give you the link where you can get these codes, but also from here I can go through these codes very easy so that you can stop anytime when you want. This is the function for make tree. This is the function for insert anywhere. The function for insert anywhere. This is the function for in order, the function for pre or post order, the function for search for a node, the function for destroy the tree, the function for finding the mean, the function for finding the maximum, and also our main function. Thank you so much. Thank you for watching this tutorial. See you next time.